So, hello and welcome. This is the next bit of it. Okay, so this is question 11. Now, I did pause the video because obviously there's different type of topic. Well, different topic even. Trying to think of the word there. And we're told a couple of key bits of information now, some of which you already know or should be aware at least. Okay. So the mass of the Sun is 1.99 times 10 to the 30. Now if you use the mass that is actually on the formula sheet, it's actually 2 times 10 to 30. So you will be out by a small amount, but for this question, doesn't really matter. Okay, the mass of the Moon is 7.35 times 10 to the 22 kilograms. Again, I think that's in the formula sheet. The distance to the Earth to the Sun, should know that, it's 1 astronomical unit, in other words 1.5 times 10 to the 11 metres, but it's just easier to write 1 AU on the board. The Earth to the Moon is 3.84 times 10 to the 8 metres, that's obviously the distance between them, and it's labelled as three different forces, okay? So basically we've got this satellite going around the low orbit of Earth, in other words just on its atmosphere line. That's how you want to register it, okay? So we're asked to compare the forces to 3 planets that all are attracted to. Sorry, we're asked to compare the forces on the space shuttle, if you want to call that, or whatever it says. Yeah, space shuttle to these 3 planets. Okay, labelled as these different forces, and the question labels A, B, C, D as different variations on which is larger, which is larger than which, and various labels. Okay, so we've got to familiarise. We're obviously talking about gravitational force, so we've obviously got to use the gravitational force equation, which is Gm1 m2 over r squared, r being distance between them, and m1 and m2 being the respective masses of the planets and the shuttle. Now, a couple of things we can do straight away, okay? Maybe to make it easier for yourself, doesn't necessarily make any difference, just makes it look a bit neater. Okay, so we know the mass of this, because obviously m1 times m2, one of them is always going to be the same depending on which one you pick the mass of the shuttle for. That's not going to change when we're looking at the force between the shuttle and the Moon and the shuttle and the Earth. It's not going to change the mass of. So you can just get rid of one of the masses, whichever you chose to be the mass of the shuttle. Okay, so we've got F is equal to G. You could also actually get rid of G, because G is technically a constant and it will be the same for every single force. Okay, for every single force, because it's a gravitational constant, it will never change. So the only 2 variables we have really are the mass of the planet and the distance between one planet and the space shuttle. Okay, now you could immediately work it out, okay, or you could logically think about it and add to working it out as well. Now, they wouldn't have told you the mass of the Sun and the mass of the Moon if they didn't want you to work out that, but they've not really told you, the mass of the Earth, which is for a couple of reasons. One, don't really need it, okay, because I'll explain in a second. And the other reason is logically, it's just in the formula sheet basically. Okay, so the logical reason why they're not giving you the mass of the Earth, well, why they're not giving it, not just being lazy, although it probably is part of it, it should be the biggest force. Fe should definitely be the biggest force, and that being, it's in low orbit around Earth. If it was low orbit around the Sun, then the force due to the Sun would be the greatest. So straight away, we know, because the Earth isn't the smallest, it's bigger than the Moon, but it's smaller than the Sun, so it's in between the 2. But because it's so close to the Earth, okay, the distance is very, very small. So therefore, the mass between the, it's going to be the biggest. Okay, it doesn't take. You could work it out, okay, but you would find that is the case. You could do that if you wanted to make sure I'm not completely insane. Okay, so we know the Fe has got to be the greatest. Okay, so straight away you can look through the alternate options and go, well, which is going to be definitely incorrect? Which says the force of the Earth is not the biggest gravitational force. Okay, so you can straight away rule out B and D. Okay, because they both say that well, one says the force due to the Sun is the greatest, and one says the force due to the Moon is the greatest. Now, obviously, you should realise out of all of them, if you didn't realise the mass, the force due to the Earth was the greatest, you still wouldn't think the force of the Moon, because it's further away. Well, it's not further away. It's quite far away, and the mass of the Moon is very, very small. Okay, it's times 10 to the 8 less than the Sun. Okay, and it is less than the Earth as well. So therefore, it wouldn't be the mass of the Moon. So you can straight away get rid of D and B, because I said the force due to the Earth is greatest, so it's out of A and C. So if that's all you realised, okay, that the force due to the Earth is the greatest, but couldn't work out the other two because you didn't realise this, or just had run out of time, okay, then you can straight away go, oh, it's going to be A or C if you run pressure on time, okay. So if you've done that, then you can already say, well, it's either going to be the force of the Sun that is greater than the mass of the Moon. So basically what you're doing now, FE is a bigger, so all you're doing, you're not calculating FE, you're just working out FM and FS, okay, using this formula, okay, where you put the mass of the planet and the radius, obviously you have to square it, radius, sorry, not the radius, the distance between the planet and the, sorry, just take this, hello? Sorry, I just had to check something. I knew I was right, but I've wrote it all down on the whiteboard as I was working out. I thought, well, what's the point in rubbing it off? Okay, so as I was saying, the force due to the Earth must be the greatest. So all you have to do is work out the force due to the Moon, Fm, and work out the force due to the Sun, Fs. Okay, so you do the mass over the distance between the two squared. Okay, so the force due to the Moon is, well, the mass of the Moon, which is 7.35 times 10 to the 22 kilograms, over the distance between the Moon and the satellite, and we're told it's in lower orbit around Earth, so the distance you have to do is Moon to the Earth, or Earth to the Moon as I've labelled it, which is 3.84 times 10 to the 8 all squared, because we're squaring the distance from the Earth to the Moon, okay, and you follow the same pattern for the Sun, okay. Now, in the reason I paused it and wrote all this up is because in my model answers here, the person who's wrote them, okay, I do check them, but obviously they're likely to be right, but in this case they're not, okay, he didn't square the distances, and he got exactly the same answer in terms of this. Now this is where, if it's a multiple choice, sometimes it's better, because if you make a mistake in converting units, you'll get a correct answer. As in this sense here, because he hasn't squared the distance, but he's still got the same answer. So just be aware that when you're using this equation, you do have to square the distances, because that was probably just pure luck on his end. Okay, so do be aware of that. Okay, because this answer would have been calculated if you hadn't squared the distances on the bottom. Okay, and as I said, if you really did want to, you could work out the force due to the Earth, but well, it's on the Earth, so what's the distance you're going to use? Okay, there's not really a distance there, apart from the radius maybe, but it's not actually on the surface of Earth, so it gets a bit confusing. Okay, so as long as them two are the right way around, you can think, well, obviously the force due to the Earth is going to be greater, so that must be the greatest force. Okay, so that was question 11, and that was A. Okay. Now this, question 12, is again a very common question in the sense that, just like when we were doing the springs before, I think it was question 10, yeah, question 10, we have to use an equation we already know and adapt it when we're comparing to different things that use, I say things, use the term generally, when we're comparing to different things that use the same equation. So in question 10 we were using the two springs, okay, we were using one equation, and one setup had one spring, another setup had two springs in parallel, okay, and we said, well, what is the time difference relative to the single spring, okay, whereas in this question, question 12, we're not using springs, we're using gravitational field strength, okay, and you should be aware, obviously, that the gravitational field strength equation is equal to F over mg, G is equal to F over m, okay, so in other words it's gm over r squared, okay, so therefore what you have to do is think, well, take out the key bits of information that's given to us and then work out the question. So I'm just going to get rid of all of this crud on the board here, if I can just find something to rub it off with. See how the camera's doing for recording. Yep, it's alright. Okay, so that's the key equation you need to use, and we're comparing the gravitational field strength at the Earth and the Moon. Okay, it says the gravitational. Oh, sorry, it's not just asking about the gravitational field strength. Sorry. So it says the gravitational field strengths at the surface of the Earth and the Moon are 9.8 kilograms and 1.7 kilogram respectively. So obviously the 9.8, that's equal to G subscript Earth, okay, the gravitational field strength of Earth, and 1.7 is the Moon. Okay, now it's worth just trying to remember them in your head, because you might get a question that says what's the gravitational field strength of the Moon, and it gives you some figures relative to Earth. Okay, so it might be worth just noting that just for future multiple choice questions where it might get you to work that out. Okay, so you can know whether you're right or not. Okay, so it says the mass of the Earth is 81 times the mass of the Moon. So I write this as an equation. So mass subscript Earth is equal to mass subscript Moon times 81. What is the ratio of the radius of the Earth to the radius of the Moon? So therefore it says, using this information, these two bits of information, work out this. Okay, and it says the radius of the Earth, radius of the Moon. So it's saying divide the radius of the Moon, sorry, divide the radius of the Earth by the radius of the Moon, so it's a ratio, and what does that come to? Okay, so what we've got to do is work out the radius of the Earth and radius of the Moon, and I'm pretty sure it gives you the radius of the Earth, but we better using it for the, it's not multiple choice. I think it, I'm not sure it gives you the radius of the Earth actually, does it? I think it does. Yeah, you could either work out the radius of the Earth and then obviously just go from that and work out the radius of the Moon, but it's probably easier to do. Yeah, you are going to need to work out. Yeah. So it's obviously going to be used from this equation here. Okay. So what do we know? Well, the radius, the obviously we know G and we know M. Okay. So what we've got to work out is, I don't think we are given the radius. So we're given the radius of Earth. That's good. Sorry, just pause the video. Just check, make sure you are given it. Sorry, I've attempted this question a few times and I can't really explain it any better than this. Okay, so it's question 11, or 12, I don't know, whatever question it is, and it's asking you to get the radius of the Earth over the radius of the Moon. So yeah, it's question 12, no, I was thinking. So it's given us two statements here that we need to use to enable us to actually work this out, okay? Because, well, we are told the diameter of the Earth and the mass of the Earth, but we're told nothing about the Moon, okay? So we need some help with some statements, okay? So it says the gravitational field strength of the Earth, obviously we know 9.8, gravitational field strength of the Moon 1.7, might not be aware of that, okay? We're also told that the mass of the Moon, the mass of the Earth is 81 times the mass of the Moon. Okay. Now, there's no equation for mass of the Moon that we can use. Okay, apart from to find mass of something. Obviously, you know it's the weight over the gravitational field strength coming from the W equals mg. But because we're considering a planet and not something on a planet, we can't use that. Okay. So what do we do instead? Well, we know there's an equation for gravitational field strength, which we can obviously use from the force of gravitational attraction. So you've got with that to fit. Now I've come up with two equations that basically say that. So we've called it equation 1 and equation 2. And I put obviously 9.8 is equal to G times the mass of the Earth over the radius of the Earth squared, and then the same for the Moon. Now basically I've tried rearranging this, but my rearranging skills are kind of poor. So it's just a case of rearranging it, okay? Each equation to get this to get the subject of this one, the radius of the Earth, okay, so you're going to need to square root at some point, and then the radius of the Moon, again, you're going to need to square root at some point, and then put the two equations over each other, obviously the right way round, and that should get you your answer. You should get 3.7, which is answer A. Okay, so hopefully that was a bit helpful to you. Now, as I said, I have tried to kind of go through it before, but I made a bit of a hash of it, so I reckon I'd best just leave it, and you know, if you can do it, you can. If it was something to come up again, okay? But that's the idea. So as long as you understand the idea, as I say, I don't think it should be too much of a problem. Okay. Now, one thing I might have done, I know I've just rubbed it all off, okay, is I might have said, well, I know what G is equal to, so either we can divide both sides by G or some way cancel them, okay, and put in the mass of the moon, because we know the mass of the moon and we know the radius of the moon, the Earth, sorry. So I might have done some variation on using bits we already know, because it's multiple choice, it's not marked as in step-by-step marking, okay? So you wouldn't have lost marks for putting in bits of information that were in the formula sheet. I mean, that wouldn't, obviously it's not what they want you to do, but they can't stop you not losing marks for it. So I would recommend, if you got stuck in that question like I did, as I say, I didn't show you putting the actual values in and doing it that way, because it's not what you meant to do, and I really don't think it'd be worth my time showing you that. Okay, but just be aware that I was mentioning before about that equation, I keep pointing to an equation which just rubbed off, that you can put the values in because it's multiple choice. Don't be afraid to kind of cheat in a sense, but obviously, you know, on the step-by-step thing, they do want you to do it properly. Okay, but as I said, it doesn't really matter. Okay, so that's question 12, and I do apologise about that. Just the model answers on here I've got, he's got it right, but he's done it the wrong way around, so it's a bit of a fluke, so I do apologise. Okay, so the next two is about finding where, is about two, explain it. So we've got two masses here. One has a mass of m, and the other one has 4 times its mass. In other words, it's got a mass of 4m, okay? And we're told they're separated by a distance d. Okay? And it says the resultant gravitational field strength is 0 along the line between the centres at a distance y from the centre of star mass m. Okay, so basically, what is it saying there? Well, it's saying, where is G 0? Okay, that's not done that. Oh, that's not good. Oh dear. So how do we know where G is 0? Okay. And then, sorry, yeah, it's got to find where G is 0 and what's that ratio of y over d. In other words, we've got a point here, we just pick a point and we say that point is where G is 0. In other words, the gravitational field strength to m and 4m is the same. So what is the ratio of the distance from m to this point over the distance between the two masses? Now, obviously, it's going to be more over this side, okay, because if it was over this side, then it's going to be, basically, this is a bigger mass, so therefore it's going to need a bigger distance to have the same gravitational field strength to the point as the smaller mass does, okay? That's basic knowledge. So, therefore, it's anything bigger than half, okay, or half itself. So, because remember, y over d is just a fraction of how big this is compared to how big this is. So, if it's a half or greater, it's going to be closer to 4m than m. And we know that's wrong because that 4m is obviously the bigger mass. So therefore, that cancels down all of them straight away actually, because A says a half. We know it's not going to be a half because therefore if it was a half, these masses would be identical and they're not. B is a third, well that's less than a half, okay. C is 2/3, greater than a half. D is 3/4, ergo greater than a half again, okay? So therefore, it must be, the only possible answer is a third, okay? So straight away, there's your answer. However, obviously, there is an explanation to this. They didn't just come up with that answer randomly. So what do you have to do instead? Well, again, the only equation for G that you know that's worth it in this case is the gravitational field strength one, from the gravitational force, sorry. So it's Gm over r squared. Okay, so how do we work this out? So obviously you're going to have to put in some kind of values to this. Now this m is obviously going to change because this m represents the bigger mass. The small mass is considered insignificant because we're just working out the gravitational field strength for a point. Okay, it could be anything on that point. That's gravitational field strength. Okay, so what we do is we say we put m. We just correspond the distances to the point, to the gravitational field strength we're talking about, okay? So for m is going to be g equals g little single m, okay, over r squared, where r is going to be the y. Okay, so it's gm over y squared. So that's for the little m. For the big M, or 4m, sorry, it's going to be 4gm, because obviously g times 4m, you could say that's 4gm, looks a bit nicer, over the distance squared, which is obviously going to be, well, we haven't got a single distance and we can't put d because that's not the distance. So it's going to be this, you could call it this other distance x, okay, from the point to 4m, but we can't put x because we want to know the ratio of y over d, okay, and that's not going to be very helpful if we have an x in there. So an easier thing to do, even though it looks more complicated at this stage, is to say, well, this distance we call x is the same as saying d take y, so put in brackets d take y squared, because we're going to be squaring it, all of it, okay, not just the d, not just the y, okay. So therefore, when this, when this is equal to that, then we know this point here is going to be equal to 0. Okay? So basically, all of this equation is just making sure that these two are equal. Right? So what you have to do here is put, I'll call this equation 1, equation 2. Now if you're doing this properly, you label it like this, say equation 1 is equal to equation 2, but we're not going to faff around with that. Okay? So y squared is equal to 4gm over d take y all squared. Okay, now obviously that's a quadratic, you're going to have to expand that as you would do in a very basic maths term. Okay, so d is equal to d squared plus y squared, take 2dy. That's right, isn't it? Yep. So therefore that's going to be on the bottom. Okay, so what we're going to want to do now is try and sort this mess out, okay, make it look a bit nicer. So we want to, remember, we want to find out the ratio of d over y, okay. Sorry, what are you doing here? Yeah, because they're both gm here, we can cancel the gm's, divide both sides by gm, okay. And then, sorry, we do then. Sorry, what's it? It's the same as saying 1 over y squared is equal to 4 over d squared plus y squared take 2dy. So it's a very simple rearrangement, obviously. So simple it buggers me. Yes. So if we times this across, so if we times both sides by y squared, we got 1 over 1 is equal to 4y squared. Okay, so in other words, 1 is equal to 4 d squared plus y squared take 2dy. Yeah, this is let's see. Okay, so because we times the y squared over here, 1 is equal to 4y squared over d squared plus y squared take 2dy. So therefore, if 4 squared over d squared plus y squared take 2dy is equal to 1, therefore the top must be equal to the bottom, because it's the only way we can have a number 1 over this side. Okay, so therefore that's the equation we go with. Okay, because remember we want y over d. Okay, and the only way we can do that is by doing this method. Okay, so 4y squared is equal to d squared plus y squared take 2dy. Okay. So, bearing in mind we want y over d, 1, isn't it? Yep. So what we have to do now is try and, well, it looks like some kind of quadratic here, so factorise it, make it equal to 0 first, obviously. So it's up to you which way round you want to do it, okay, you'll get the same answer. So I think it's probably easier to bring the 4y squared over here. So d squared take 3y squared take 2dy equals 0. Lovely cold and stuff I've got from my family. Not believing me, obviously. So. But what we want to do there is factorise it. So that will get you d plus y brackets d take 3y equals 0. Okay, and we want to work out what this distance is here. Okay, so, sorry, what this y is. Excuse me. So, well, in this case, for this to be equal to 0, okay, y would have to be, no? Oh, yeah. If d plus y is equal to 0, d would have to equal to minus y, okay? And if d was equal to minus y, okay, they're going to be the same. So you could either think of it as just saying, well, they must be the same, so you could just say the 1. So therefore, y would have to be minus a number, and you can't have minus a distance, okay? So that can't work. I mean, in my model answers he's done, then you divide both sides by minus y, so therefore d over y is equal to minus 1, which you can't have. Okay, you could just say you can't have a minus distance, so that can't be right. So, and then the other possibility, okay, is d take 3y is equal to 0. Okay, so obviously if we've done something right here, this must be right. So therefore d is equal to 3y. So you divide both sides by y, so d over y is equal to 3, and that must be the possibility. Okay, that must be a right answer because it's positive and you can't have a unit 3. Okay, so therefore this says d over y, okay, is equal to 3. In other words, d over y is equal to 3 over 1. But we want y over d, so you flip both sides of the fraction, so therefore y over d is equal to a third, which is answer A. Okay? So I agree that's a very, very long and complicated way of working it out, which is why I think my idea, okay, so if that was a multiple choice, so if that was a section B question, okay, you can see very easily why you'd need to do that. However, if it was a section A question, like it is here, weirdly enough, you can see how my idea of logical thinking saves you so much time, because that's quite a complicated question, I think, and I think it's a lot easier just to go, right, well, we know that it's got to be closer to m, okay, so therefore the ratio of y over d must be less than a half, or can't be equal to a half, okay, so that signals out the other 3 straight away. So just like that, just by thinking of that one thing, you know it's got to be A, okay. Now if it said prove this, or as I say a section B might, then you would need to do that, but otherwise you wouldn't, because I'm pretty sure when I did this question, okay, so I'm going off my model answers here, when I first attempted this question, I got stuck on the rearranging, like I did then, because obviously I haven't looked at model answers since, so this is just doing it and then looking at them if I need some help. So, because obviously I'm a genius, and obviously I wrote them model answers, but you get the idea, okay? So it is quite a difficult question, but I would recommend the idea of logical thinking, which I know is hard in the exam, but it's probably even harder to try and think of that in that small gap that you've got in the papers, okay? So just a heads up there to question 13. Alright, so question 13 was, just make sure it wasn't, oh sorry, that was option B, sorry, do apologise. So 13 was option B. So here's another one of them questions that is a comparison question. So again, we did one, well, tried to do one before, hopefully I can do it this time, where it's using an equation and for one planet or for another. Okay, so we're told that the Mars has a diameter of 0.5 of the Earth. Okay, so the first thing I would do is write that down in kind of a note form, because as I say, you don't have that much space. So it says the diameter of Mars is half of the Earth. So it's way around to write this. Diameter of the Earth. Or you could write the diameter of Earth is 2 times the diameter of the Moon. Okay, so obviously you can write that way around or the other way around. I think that looks a bit neater, but it says it doesn't really matter. And a mass 0.1 of the Earth. Okay, or you could write the mass of the Earth, okay, is equal to 10 times the mass of the Moon. Okay, so you could write them the other way around. I've just wrote it the other way around because it's easier for me, but you could write it obviously that the mass of the Moon is half the diameter of the Earth, and the mass of the Earth, so the mass of the Moon is 0.1 times the mass of the Earth. Either way, doesn't matter. Okay, so it says the gravitational potential at the Earth's surface is minus 63 megajoules per kilogram. Okay, so that's the thing we need to write. So the gravitational potential is minus 63 megajoules per kilogram. Okay. I remember that's kind of the potential to escape the Earth's gravitational pull. Okay. So just that's just something to remind you of. Okay, it says what is the approximate value of the gravitational potential at the surface of Mars? Okay, now this is where the equation comes into play. Now obviously it's giving you the gravitational potential equation, so we're likely going to have to use that one. So let's see what that is, and hopefully we can use diameter or the radius. Okay, at the Earth as well. Okay, so it's the, if you look in the formula sheet, it's minus gm over r. Now there's something that I'm pretty sure it says in the, well, it does say in the examiner's report, or I'm pretty sure it does, that a lot of students thought, well, its diameters of the Earth is half, so we need to half it again. Or in the case of I've done, the diameter of the Earth is 2 times the diameter of the Moon. So if we work out the radius, then it's going to be 4 times the radius of the Moon. Well, it isn't half like that, okay? It's going to be the same ratio. So just stick with that, okay? So that's the same as saying the radius of the Earth is 2 times the radius of the Moon, okay? Don't need to change that, the ratio of it, okay? Just because we're halving it, we're halving both, okay? So if that doesn't make sense to you, you weren't confused on it, don't worry about it. If you were confused on it and it helped you, you're welcome. Okay, so we know for the Earth, okay, so the first thing I would do is put equation 1 and put it in the context of the Earth, okay? So we know it's minus 63 megajoules per kilogram, okay? So we know it's equal to minus g times the mass subscript Earth over the radius subscript Earth. So put that as equation 1. Equation 2 is for the gravitational potential of the Earth, Moon, which we don't know. It's equal to minus g times the mass of the Moon over the mass of the radius of the Moon. So again, this is one where we're going to be trying to work out the gravitational potential of the Moon. Okay, so sorry, Mars. What am I doing? Sorry. I thought, where did I get Moon from? Mars. And that's also Mars. Okay. So what have we got to do here? Well, what we've got to do is try and figure out, convert them. Okay, so they say the same thing. Okay. So you could either convert them both to say the mass of the Moon, or both to say the mass of the mass of Mars. Oh God, so why do I keep saying Moon? I don't understand. So I've got it here. I need to get rid of that Mars. Okay, so it's up to you which way around you do it. I would, because of the way I've written it here, convert them both to the mass of Earth. Okay, so times 10 times the mass of the Mars and the radius is 2 times the radius of the Mars. Okay, so in that context we now know, because that is the radius of the 63 megajoules per kilogram. Okay, because we know this, we've adapted this now to say exactly the same as the mass of Earth and the radius of Earth, but we've put it in the context of the mass of Mars and the and the radius of Mars. Okay, so they both have the same value, so therefore equation 1 and equation 2 are equal to the gravitational potential of Earth, which is minus 63 megajoules per kilogram. Okay, so that's all we've done. We've just put it in both in the context of Earth. Okay, so we both know they're equal. So therefore we can say equation 1 is equal to equation 2. Okay, so therefore once we've done this, it's asking for, it's asking, what's your approximate gravitational surface at the surface of would it be worth doing it that actually? Sorry. Actually, no, I think we should do it the other way around, yeah. I've done it the wrong way around. Do apologise. So do it the other, but using the other idea, okay? So, is it worth just getting rid of all of this? No, sorry, we're not doing a ratio, so that's not worth it. Do apologise. We know that the diameter of Mars is half the diameter of Earth, okay? So therefore, if we divide the radius by 2, you have to divide the radius by 2 and times the mass of the Earth by 0.1. Okay, that's the same thing. Yeah, this is the way to do it. I'm still overthinking it. Okay, sorry. So we know that for the Earth it's minus 63 megajoules per kilogram. Okay, but you convert it into the the mass of the Mars and the radius of Mars. Okay, so we see what had, and therefore we can see what we need to change the minus 63 megajoules per kilogram. Okay, so we're timesing the mass by 0.1 and we're dividing the radius by 2. Okay, so it will half in the bottom bit, so you could just say, well, it's the same as timesing the top bit by 2. Okay, so therefore we're alternate by 0.1 times 0.2 times 0.1 times 0.2. In other words, we're timesing this whole equation by 0.2. So that's all we're changing this entire equation by. Okay, and we know that this bit is equal to minus 63 megajoules per kilogram, and we times it by 0.2, so we need to times this side, which was minus 63, by 0.2 as well, to get the gravitational potential of the Moon. So we do minus 63 megajoules per kilogram times 0.2, and that'll get us the gravitational potential of the Mars. Okay, which you should get as minus 13 megajoules per kilogram. Okay, so sorry, you can see I did a very long way around there. Do apologise, but that is the idea. Okay, so that is question 14, which is option A.